Hi guys, welcome back. So today we are recognizing oxidation and reduction reactions. We're going to see how we can recognize oxidation and reduction reactions. So we're literally picking up from where we left off yesterday. So yesterday, let's do a quick recap. Yesterday we learned how to assign oxidation numbers, and we realized there's three rules to assigning oxidation numbers. So the first rule is that if the atom is by itself, that the oxidation state is zero. The oxidation state of an individual atom is zero if it's by itself. It's zero. Remember, if there's no, I'm going to repeat this, if there's no element next to another element, there cannot be a transfer of electrons. Where is the transfer going to go? So it needs to be in a companion. It needs to be in a compound. All right. Single replacement reactions are always redox. Always. We're always going to see that. And you're going to see that today. Double replacements are not. Sometimes as we go on, you're going to realize that it is possible for a double replacement reaction, but there's going to be an issue with it. And then the total oxidation state of all atoms in a compound is zero. So the overall total oxidation state for a compound is going to be zero, but within that compound, each element has its own individual oxidation state. So that's where we left off yesterday. So our do now, we're going to go ahead. I'm going to do this real quickly. We're going to go ahead and assign oxidation states for this. Now, once again, I'm using the periodic table that I have on my phone. I'm not going to use the one that we have on this slide because there's going to be a lot of flipping back and forth. So I'm going to use the one I have on my phone. Remember, you must have a periodic table. You can go to kentchemistry.org to download it for free, or you can go to the New York State website and download it for free as well. But you should have a physical copy. It's better to work with a physical copy. So let's find the oxidation state of NaOH. First of all, it's in a compound. So that means the overall oxidation state needs to be zero. So I'm going to do NaO and then H, right? And I'm going to find out how much of each element that I have. Let me see if I can connect it right here. There we go. I'm going to have how much of each element that I have. I have one Na, I have one O, and I have one H. Perfect. I always like to start with oxygen because oxygen, I already know off the top of my head, has an oxidation state of -2. So 1 times -2 is going to give me a -2, right? Then, as I looked on my periodic table, I know that Na has a +1 oxidation state. So 1 times +1 equals a +1. Now, what I did right off the bat was I went and I found the elements that only had one single oxidation state. Because obviously, if it only has one single oxidation state, that has to be the oxidation state. So, we have -2 plus 1 plus +1, which is going to leave us with -1 left. So that means H has to be something that cancels out -1. Well, to cancel out -1, you're going to need a +1. So that means H needs to be a +1. I just need to check on my periodic table to see if H has a +1, and yep, H does have a +1. H also has a -1, so that's how I was able to differentiate which one I was going to take. So +1 plus -2 plus 1 will give us 0. And then we've satisfied one of the rules. The overall total oxidation state for the compound would be 0. Let's go ahead and do it for HCl. I'm going to work right here. H and then Cl. I have one atom of each, so there's 1 and there's 1. But like we said, H has 2 oxidation states, which is +1 and -1, while Cl has 3 oxidation states, which is +1, -1, and I believe it's +3. Right? So we need to see now, because they have multiple. For H, I'm going to go ahead and use the first one that pops up, so which is +1. So 1 times +1 is going to give me, obviously, a +1. So that means Cl, to cancel out +1, has to be a -1. Exactly. I just need to look back on my periodic table to make sure that Cl have a -1, and because it does, this works. Now, some of you are like, okay, but what if you didn't pick +1 for H? What if you picked -1 for H? Alright, so let's go ahead and try that out. So 1, we still only have 1H. But then we have -1 over here, which is going to be 1 times -1 is going to give us -1, obviously. And then we still only have 1 Cl. But now Cl, to cancel out this -1, needs to be a +1 right here. And does Cl have a +1? Yes, it does. So that still ends up working out and canceling out itself. However, know this. Hydrogen is mostly associated with as a positive proton. So this is where it becomes a +1. It's always associated as a positive proton. All right. And then we have Sn on our last one over here. Now, Sn's oxidation state will equal to 0. Exactly. Sn's oxidation state will equal to 0 because it's by itself. If it was with another element, like if I had SnO2 over here, it would be possible because obviously there's going to be a transfer over here. But because this is not there and it's by itself, its oxidation state is 0. So that's our do now for today. Now, one thing you need to know is that when it comes to oxidation and reduction reactions, we're working with oxidation, ox, I like to call it, and then we are working with reduction, and I like to call it red, right? So, in the reading, you're going to realize that we in chemistry always come up with an acronym. Yes, we're cute like that. So, we come up with the acronym, and for ox, our acronym is LEO, right? And then for reduction, our acronym is GER. And what it means is that lose electrons, oxidize. Gain electrons, reduce. I'm going to say that again. I'm not going to write it because it's going to take me a while. Lose electrons, oxidize. Gain electrons, reduce. Right? Now, this pretty forward, really pretty forward. But one thing you need to remember is that we're working with electrons. I don't know what's going to do over there. We're working with electrons. Electrons are negative. So because we're working with electrons, when we lose oxidation, when we lose electrons, we become more positive. But when we gain electrons, we become more negative. If you keep that concept in mind, you should be able to work your way through this, right? So I came up with this little check sheet to help, a checklist to help you out. Use it, always refer back to it. I would actually write it on the side so that you know what you're working with. So my checklist says elements by themselves have an oxidation state of 0. Elements in a compound have an oxidation state of total oxidation state, keyword total, oxidation state of 0. When we oxidize, we have an increase in oxidation number, or it is positive. And when we reduce, we have a decrease in oxidation number, or it is negative. So let's see if we could use our checklist for this problem. So this is where we left off yesterday. Some of you did hit me up and you said you were a little bit confused. So we're going to use our 3 rules. Element by themselves have an oxidation state of 0. So Sr is by itself. This 2 is not important to me right now. And O is by itself. Once again, this 2 is not important to me right now because oxygen is by itself. There's no other element. So they have an oxidation state of 0. All right. Now, I have a compound here. So I did my first part of my checklist. Then they have a total, elements in the compound have a total oxidation state of 0. When this happens, I like to go ahead and put this over here. I know that I'm working towards 0 when I add them up. This 2 means nothing to me over here. So let's go ahead and do what we did for our do now for SRO. So we have SR and then we have O. For each element, I have 1 of each. And then I know that oxygen has an oxidation state of -2. So that means 1 times -2 is going to give me, obviously, -2. And then 1 time, now to cancel out this -2, SR needs to be a +2, exactly. So if it needs to be a +2, I just need to make sure that SR has a +2. And when I look on my periodic table, yup, SR has a +2. So +2 plus -2 will cancel each other out and give me 0. So I've satisfied my second point of my checklist. Now it's time for me to decide which one is oxidized and which one is reduced. So I'm going to write this out over here, and I'm going to be comparing my elements from my left to my right. I'm going from my left to my right. If we were in class, I would have us draw brackets to compare them, but because we're not, and to make it a little bit easier on our eyes, we're going to go ahead and just compare it over here. So SR went from 0 to positive 2. While O went from 0, I'm starting from my left side, and I'm only focusing on the oxidation state, to negative 2. So, remember, when I lose electrons, I become positive. When I gain electrons, I become more negative. So, from 0 to plus 2, I'm becoming more positive. So, that means I lost electrons. Meaning, if I lost electrons, I am oxidizing. And then from 0 to negative 2, well, if I'm becoming more negative, that means I gained more negative particles. So I gain over here, and we are reducing. And that's it. So let's go ahead, let's try 2 more problems, and then maybe 2. Let's see what the time gives us, and then move on to your own practice. So we have Li at 2Li plus S gives us Li2S. All right, so we're starting off the first part of our checklist. We have 0 and we have 0 because they're by themselves. Now we know Li2S has to give us a total oxidation state of 0. So it's going to find out Li2S. So Li has 2, S has 1. Now when I check on my periodic table, Li has an oxidation state of plus 1. It only has that one oxidation state. So plus 1 times 2 will give us plus 2. Always keep your symbols there. Don't forget them. They're very important. So that means to cancel out plus 2, S needs to be a negative 2. Exactly. And does S have a negative 2? It sure does, with amongst other things. So that's how we determine the oxidation state. So we have negative 2 here. So plus 2 plus negative 2 will give us 0. So we satisfied the second part of our checklist. So we're good with this part. Now let's do our comparison. I was like drawing a line here. So Li is going from 0, 0 to plus 2. And then S is going from 0 to negative 2. Well, from 0 to plus 2, in chemistry, that means that we lost electrons because we're becoming more positive. So when we lose, we oxidize. I'm just going to write my ox. And then when from 0 to negative 2, it means that we gained electrons because electrons are negative. So the more negative I become, that means I have more electrons. So that means we gain electrons. That means we are reducing. Exactly. All right. I'm probably not going to be able to get through this one, so I'm just going to do it without saying any words. Now tell me what my answer is going to be for this one in the comments, and have a good day, guys.